Okay, so in this next question, we're asked to determine the intervals over which the function is increasing, decreasing, or constant. And we're given this function here, f of x, and it's defined piecewise, meaning it's defined in 3 different pieces depending on what our x values are. It could be a different function. So for example, when our x value is less than or equal to 0, our function is going to be represented by x plus 3. When our x value is greater than 0 but less than or equal to 2, our function is going to be represented by 3. And when our x value is greater than 2, our function is going to be represented by 2x plus 1. And of course we have this graph here that graphically depicts this piecewise defined function. Now, you want to remember that when we're determining intervals over which the function is increasing, decreasing, or constant, we want to look at the x and f of x ordered pairs. So let's say I pick 2 points on the graph, x1 and f of x1. And remember, f of x1 is basically a stand-in for y1. It's the function evaluated at x1, which would correspond to a y value on the graph. And let's say my other point is x2 and f of x2. And let's say this point right here is going to be my x1, f of x1, and this point is going to be x2, f of x2. So the rule that we learned is that if f of x2, if this point is greater than the y value of this point, then the function is increasing. If f of x2 is less than f of x1, then the function is decreasing. And if f of x2 equals f of x1, the function is constant. So, knowing that, let's solve the problem. So our first piece is x is less than or equal to 0. So that's kind of going to be this chunk right here. Obviously, you would continue beyond what's shown in the graph, but it goes from basically negative infinity all the way to this 0. Now, if we look here, this line is constant, meaning whatever rule we manage to pull out of it will be constant on that entire interval. And like I just showed in the example I just gave, f of x2, this point, will always be greater than f of x1 because this function is increasing at a constant rate. So, because basically it looks like this, we know that for any x1 f of x, we know that for any x1 and f of x1 and x2 and f of x2 pairs that we pick, x2 and f of x2, or rather f of x2 will always be greater than f of x1. So we can say that it's increasing on this interval. So in our pre-calc interval notation, we're going to write negative infinity to 0, and we're going to close the brackets. So the reason we leave it open for negative infinity is because you can't really represent negative infinity by a number, so you can't say this is inclusive to negative infinity. So we have to do this open bracket here. It's a closed bracket for 0 because this is less than or equal to 0 in this piece right here, meaning that 0 is included here, and it will be increasing up to and equal to 0. Now if we go to the next interval, which is going to be basically between 0 and 2, so right here, we can see that it's this line right here. And they've gone and drawn out the dots for us, and we can see here that f of x2 is equal to f of x1. So that would say it's constant on that interval. So I'm just going to write increasing to keep this all organized, and then constant, and that's going to be constant from 0 on an open bracket to 2 with a closed bracket. And it's open bracket for this one because 0 is not included in this interval. You can see there's no underline here, so it's not included, but 2 is included because there is that underline meaning up to and equal to 2. Another way you could check your answer is just by plotting points. So for example, if I plot 1, for example, well, that's between 0 and 2, so that would be 3. And then if I plot 2, well, 2 is equal to 2, so it'd still fall under this function, so it'd be 3. So it would be constant, and you could get the answer from that, if that makes any sense. Now for the last and final interval, from 2 to basically infinity, because it would go beyond this. Once again, we can see that just like with this piece down here, this is just going to keep going up constantly because it's defined by 2x plus 1. So again, you can pick any 2 points on this line. You can pick any 2 points in this 2x plus 1 function. F of x2 will always be greater than f of x1. So we know that it is also increasing from 2 to infinity. And again, open bracket on infinity because you can't represent that with a number, and open bracket on 2 because 2 is not included in this interval. And this like widened out U shape is called a union. It basically means and. So I'm saying it's increasing from negative infinity to 0 and on 2 to infinity. So that would be my final answer. Okay, so in this next question we are asked to graph the function and determine the intervals for which f of x is greater than or equal to 0. And the function we're given is f of x equals 4 minus x. So I'm just going to graph the function first, and then we're going to determine the intervals. So at x equals 0, 4 minus 0 is 4, so we're going to have a point right there. At x equals 1, 4 minus 1 is 3, so we're going to have a point right there. X equals 2, 4 minus 2 is 2, we're going to have a point right there. And then x equals 3, 4 minus 3 is 1, we're going to have a point right there. And then x equals 4, 4 minus 4 is 0, so there's a point. And at x equals 5, our point is going to be at negative 1. Now if we continue over here to negative 1, 4 minus a negative 1 is the same thing as 4 plus 1, which is 5. So we're going to have a point right here, and at that point it's going to go off the graph after that, so I'm just going to stop there. I'm going to draw my rough line. So now we need to determine the intervals over which f of x is greater than or equal to 0. So knowing the property y equals f of x, knowing that f of x is basically a stand-in for y, we basically need to find where y equals 0, and then everything above that is going to be our interval. So y equals 0 right here on this, basically on the x-axis line is where y equals 0. If we go below that, y is going to be negative. So everything above this point will be greater than 0, and then of course this 0 point will be 0. So in interval notation, going from left to right, negative infinity to 4, and including 4, because it is 0 at 4. And now remember, when I write this interval notation, it's going based on x values. So negative infinity refers to an x value, even though you can't represent it as a real number. Just imagine this number line extending way, way, way out. And then kind of as you get closer and you get into these numbers, and then right here, it's like x values, and it goes down to this x value of 4, where y is equal to 0. So that would be my answer. Hopefully that explanation of interval notation made sense. So in this next problem, we're asked to do the exact same thing, except this time our function is 9 minus x squared. So starting as 0, 0 squared is 0, 9 minus 0 is 9, so it's going to be up here. X equals 1, 1 squared is 1, 9 minus 1 is 8, so it's going to be way up there. X equals 2, 2 squared is 4, and 9 minus 4 is going to be 5, like that. And then 3 squared, or x equals 3, 3 squared is 9, 9 minus 9 is 0. So it's going to be like that. Now, what we know about parabolic functions like this that have a negative in front of x squared, it means they open downward, meaning that the peak is going to be up here where x equals 9, and it's going to cascade down like this, like a classic parabola. I drew that poorly, hold on. Something like this. And we know that these are symmetric about the y-axis, meaning that whatever points we have on here we can reflect over here, because squaring it will make it, if it's a negative x value, squaring it will make it positive. For example, x equals negative 3, negative 3 squared is positive 9, 9 minus 9 is 0. So we can do that and get a more accurate shape of the curve there. So now we can see that f of x equals 0 in this kind of cone-shaped region here. So in interval notation, that would be negative 3 to 3, and both of them would have closed brackets, because at 3 and negative 3, f of x does equal 0. So that would be my answer. The exact same thing to graph the function and determine the intervals over which, for which the function f of x is greater than 0, greater than or equal to 0, and our function this time is f of x equals the square root of x minus 1. So with this one, we cannot start at 0 this time, because 0 minus 1 would be the square root of negative 1, which is the imaginary number I, but because we're not dealing with imaginary numbers in this case, we're only dealing in the real number category, we're going to have to start at 1. So at x equals 1, 1 minus 1 is 0, and the square root of 0 is 0. So then we get to x equals 2. 2 minus 1 is 1, the square root of 1 is 1. Then we would get the square root of 2 at x equals 3. That's going to be a decimal number. And so would the square root, and so would x equals 4, because that would be the square root of 3. But at x equals 5, 5 minus 1 is 4, and the square root of 4 is 2. So then we get that our graph looks like that. And so we would say that in our interval notation, we would say that it's greater than or equal to 0 from 1 to infinity. And if it's not clear why it's infinity, just pick increasingly larger numbers for x, and you'll see that the y value will not go below 0. So for example, if we pick 10, x equals 10, then that's the square root of 9, which would be 3. If we pick 145, x equals 145, 145 minus 1 is 144, and the square root of that is 12. So it would just keep going up and up and up. So my answer is 1 to infinity. Okay, so in this next question, we're asked the exact same thing, and this time the function is technically negative 1 times 1, okay, let me rephrase that, negative 1 times the quantity 1 plus the absolute value of x. So seeing as I did the last 3, I'm going to go ahead and give you an opportunity to try this on your own, and you can come back when you're finished and see if you get it right. So assuming you pause the video to practice the problem and now you're finished with it, let's see how you did. So starting at 0, starting at x equals 0, the absolute value of 0 is still going to be 0. 1 plus 0 will be 1, but then we have to make that a negative. So it'll be down here. And we make it a negative because this negative 1 is multiplying to whatever the result of this equation is. So then when we have x equals 1, the absolute value of 1 is 1, 1 plus 1 is 2, and that becomes negative 2. Then for x equals 2, the absolute value of 2 is 2, 1 plus 2 is 3, and then that would become negative 3. Now x equals 3, once again, 1 plus 3 is 4, negative 4. And then for x equals 4, the absolute value of 4 is 4, 1 plus 4 is 5, negative 1 times that, negative 5. Then we go to negative 1, x equals negative 1. Well, this absolute value of negative 1 is 1, 1 plus 1 is 2, and negative 1 times 2 is negative 2. So we're going to be down here. And we see a similar situation to what we had with the parabolic problem before. When you have an absolute value equation like this, it is also symmetric to the y-axis, meaning we can just flip these points over here and do this. And we get this. And now we can see that the function is never greater than or equal to 0. It's always less than 0. So the interval does not exist. I'm going to write DNE. It stands for does not exist. So yeah, that would be my answer for that one. Okay, so in this next question we're asked to find the average rate of change of the function from x1 to x2. And our function is f of x equals negative 2x plus 15. Our x1 is 0, and our x2 is 3. Now, this problem may seem confusing or challenging at first, but you just need to look at the wording in the instructions. The average rate of change is another word for slope. It's saying find the slope of the function from x1 to x2, or rather from x2 to x1 would be more reasonable. So we know that to find the slope is, the formula for the slope, well actually I shouldn't even write it down, you should have it memorized. If you don't have it memorized, you should write this down. The slope is m equals y2 minus y1 over x2 minus x1. It's the rise over the run. So we're looking for the corresponding y1 as well as the corresponding y2. And you may be wondering how we're going to do that. Well, we're given a function here, and we're given an x value. So we can plug this x value into this function, and that result will be our y value. So that's how we can find our y1 and our y2. So f of x1, which you can also write as f of 0 if you want to, will be negative 2, and then we're going to replace all x's with the x1 value, which is 0. So negative 2 times 0 plus 15. Anything times 0 is 0, and 0 plus 15 is 15. So our y1 value is 15. Now we're going to do the same thing with y2, or x2 rather. So you can write f of x2, or you can write f of 3, and you're going to want to replace all the x's in the equation with 3. So negative 2 times 3 plus 15. Negative 2 times 3 is 6, and 15 minus 6, which you can rewrite it as, is 9. So that's 9 right there. Now we have x1, y1, x2, y2, and we can do m equals y2 minus y1 over x2 minus x1. So that's going to be 15 minus 9 over 3 minus 0. 15 minus 9 is 6, so we have 6 divided by 3, which is 2, meaning that the average rate of change, or the slope, from x equals 0 to x equals 3 is 2 for the function f of x equals negative 2x plus 15. Okay, so just a quick correction. Instead of doing y2 minus 1 here, y2 minus y1 here, I accidentally did y1 minus y2. So y1 is 9 minus 15, x2 is 3, and x1 is 0. So that's negative 6 over 3, which is negative 2. And that would be your answer. Okay, so in this next question we're asked to do the exact same thing, except now our function is x squared plus 12x minus 4, and our x1 is 1, and our x2 is 5. So we're going to do the exact same thing we did in the last problem. We're going to plug in these points of this equation to get our y1 and our y2, and we're going to use our slope formula to solve the problem. So for f of x1, we're going to plug in a 1 wherever we see x. So 1 squared plus 12 times 1 minus 4. That's going to be 1 squared is 1, 12 times 1 is 12, and that negative 4 is just going to stay there. So then that's 13 minus 4, which is just 9. So this is 9. Then when we do x2, we're going to plug in 5 wherever we see x. So 5 squared plus 12 times 5 minus 4. 5 squared is 25. 12 times 5 is 60. And that negative 4 is going to stay the same. 25 plus 60 is 85. And we have 85 minus 4, which is just 81. Then when we go to do our slope, we're going to do y2 minus y1. 81 minus 9. And then x2 minus x1, 5 minus 4. So 81 minus 9, so 81 minus 1 is 80, so then that's 80 minus 8, which is 72. This is meant to be a 1, by the way, hold on. 72 over 4, which may be divisible. Let's check. So 4 goes into 7 once. Yep, it is. 30, 32, so that's 18. So our answer is 18. Meaning that this function has a slope of 18 from x equals 5 to from x equals 1 to x equals 5. Okay, so in this next problem we're asked the exact same thing, except our function now is f of x equals x cubed minus 3x squared. That x squared should actually be over here, like that, and then minus x. And then our x1 is 1 and our x2 is 3. So considering that I've done the last two problems, I'm going to go ahead and let you try out this problem on your own, and you can come back to it when you're finished and see how you did. So assuming you've paused the video and tried it on your own, let's see how you did. So the first thing I'm going to do is factor out an x from this whole thing, just to make it a little bit easier on ourselves. So it's going to be x times x squared minus 3x minus 1. Now we can see that we still have the same equation, it's just broken down a little bit more and simplified. Now let's do f of x1. So that's going to be 1 times 1 squared minus 3 times 1 minus 1. This one we can basically get rid of because it's not going to change the final result either way. So 1 squared is 1, negative 3 times 1 is negative 3, and then that negative 1 is going to stay there. Then 1 minus 3 is negative 2, negative 2 minus 1 is negative 3. So our y1 is negative 3. Then our f of x2 is going to be 3 times the quantity 3 squared minus 3 times 3 minus 1. 3 squared is 9. 3 times 3 is 9. And then we're going to be left with that negative 1. 9 minus 9 is 0, so we're going to have 3 times negative 1, which is just negative 3. So both our y2 and our y1 is negative 3. So when we go to do our slope, we're going to have y2 negative 3 minus y1 negative 3 over x2 3 minus x1 1. A minus minus a negative, or subtracting a negative, is the same thing as adding. So negative 3. Negative 3 plus 3 is 0. And 3 minus 1 is 2. So 0 divided by 2 is just 0. So our slope is 0 from x equals 1 to x equals 3. So that's how I would do that one. Okay, so in this next problem we're asked to do the exact same thing, just different equation and different points. Our equation now is negative 1 times the square root of x minus 2. X minus 2 is all under the square root, and plus 5. So, and our x1 is 3, and our x2 is 11. So I'm gonna give you a chance to do this on your own, and you can pause the video and come back to it when you're finished and see how you did. So assuming you've paused the video and tried the problem on your own, let's see how you did. So our f of x1, we're just going to plug in 3 wherever we see x. So we're going to have negative 3, or negative 1 times the square root of 3 minus 2 plus 5. 3 minus 2 is 1. So we have negative 1 times the square root of 1 plus 5. The square root of 1 is just 1, leaving us with negative 1 plus 5. Oh, sorry. Negative 1 plus 5, which is just 4. So our y1 is 4. Then for our f of x2, we're going to plug in 11 wherever we see x. So that's negative 1 times 11 minus 2 plus 5. So negative 1 times 9, because 11 minus 2 is 9, plus 5. The square root of 9 is 3, so that's negative 3 plus 5, which is 2. Now to plug it into our slope formula, y2, which is 2, minus y1, which is 4, over 11 minus 3. That's going to be negative 2 over 8, which can be reduced to negative 1/4. So that would be my answer for that one. Okay, so in this next question we're asked to determine whether the function is even, odd, or neither, then determine its symmetry. So the important thing to remember here is that in order to determine whether a function is even or odd, we have to remember two key rules. So the key rule here is that if f of negative x is the same thing as f of x, the function is even. I'm just going to write e for even. If f of negative x is equal to negative f of x, then the function is odd. O for odd. And if it's neither of these, then it's neither. So this may still seem somewhat confusing, especially because we're dealing with abstract things like x and negative x and all that. So let's do it for this one. Let's see if this is even, odd, or neither. So I'm going to plug in negative x wherever I see x. I'm going to start with f of negative x, just like it says to up here, and wherever I see x, I'm just going to replace that with negative x. So negative x to the sixth minus 2 to the negative x squared plus 3. So negative x to the sixth will be just x to the sixth, because it's raised to a even power, so it's like it's basically just saying negative x times itself 6 times, and if you repeat that, if you do that out by hand, you'll find that it's x to the sixth times negative 2, and negative 2 will be multiplied by x squared, because negative x squared is just x squared plus 3. We can see here that we're left with the exact same equation as we started off with. In other words, f of negative x equals f of x. We can even point this out. We can say f of negative x is equal to f of x. That would be how you really solidify your case that this is even. So I'm going to say this is even. And I'm going to say that it's symmetric about the y-axis. I'm inclined to say that because there's an x squared and an x to the sixth. Anytime an x is raised to the power in this equation, it's even. So I feel like it would look something like a parabola type shape like this. And I can check my work by plugging in a point that would be on the left side of the vertex as well as the right side of the vertex, and I would see that they're both the same number. It would take too much time in this video if I found the vertex of each equation and then proved that they were symmetric and all that, but the answer is that it does have y-axis symmetry, and you can check this for yourself. So y-axis symmetry. I'm just going to write y-axis for short. And that would be how I do that one. So in this problem, we are asked to do the exact same thing, except our function now is x cubed minus 5x. So I'm just going to plug in, I'm going to do f of negative x, and plug in negative x wherever I see an x in the equation. So that's going to be negative x cubed minus 5 times negative x. Negative x cubed is just negative x cubed, and negative 5 times negative x is a positive 5x. Now, looking at this, it might not seem immediately clear what the answer is, but I'm going to go ahead and factor out a negative 1. And if I factor out a negative 1, this becomes x cubed minus 5x. Right? Because if we distribute this negative 1, we get negative 1 times x cubed, which is negative x cubed, and negative 1 times negative 5x, which is positive 5x. So these two are the same thing, just rewritten differently. Now it's clear, it should be a little bit clear here that f of negative x equals negative from this negative 1 times f of x. And we know that to mean that our function is odd. And I'm going to go ahead and say that the symmetry here is about the origin, because usually when you have x cubed equations like this, they look something like this on the xy coordinate plane, and they'll be symmetric about the origin, meaning that an xy point here will be equivalent to a negative x, negative y point down here. So I'm going to say odd and origin symmetry. And that's how I would do that one.